Hi students, myself Dr.Shouri Dominic. I am working as an associate professor in Vignan Institute of Engineering for Women. Today we are going to discuss about one of the important chapters in mathematics. That is, as you already know, mathematics, how important it is in engineering. Not only in engineering but also in science and technology. Mathematics plays a major role in every field. Okay, so now that is what one of the important chapters in mathematics. Now today we are going to discuss, that is nothing but Laplace transforms. What is a Laplace transform? What is the use of Laplace transform? Today now what we are going to discuss. So today now we are going to discuss about the introduction of the Laplace transform and applying the Laplace transform to the different elementary functions, and the third one few properties of Laplace transform and problems on Laplace transform. That is, we are going to apply the Laplace transform to some functions and going to get the results. Okay, and at the end of this video, so now we are going to understand how we can apply the Laplace transform to the different functions. Okay, so let us start with the beginning, the introduction part here. So the Laplace transform is an important and very powerful mathematical tool which is used to solve differential equations, especially in mathematics, but in so many engineering fields it is particularly used in control systems and control engineering, communications and signals design and signal analysis and system analysis, and most importantly in mathematics, solving differential equations. As you already know, in the differential equations we have so many types of differential equations we have. That is ordinary and the partial differential equations. It doesn't matter what type of differential equation we have, whether it is first order or the higher order, or it is ordinary differential equation or partial differential equation. It doesn't matter, but the Laplace transform is an important and excellent tool to solve any type of differential equations, whether it is ordinary or partial. It doesn't matter, but it can by using the Laplace transform we can solve any type of differential equation. Generally we know to solve the first order differential equation, depending on the type of differential equation, we have different procedures and we have different methods. As you know, wherever you can see the differential equations plays a major role in finding so many solutions for the different types of problems. That's like nothing for example, finding the temperature, the room temperature, okay, and population growth and simple harmonic motion. In such fields, and not only in that, in the physics and the quantum mechanics also we use the mathematics. And here in the differential equations, it's very important, this Laplace transform. And in the control, the Laplace transforms also plays a major role in control systems. And to analyze the control system, the Laplace transform, the different functions have to be carried out. Now we are going to discuss about the introduction, but how important and how powerful the Laplace transform in order to solve any type of ordinary or partial differential equations. We know that the classical method of solving the higher order differential equation, we have to find the complementary function and the particular integral to get the general solution of higher order differential equation. But here, by using the Laplace transform, we can find the direct solution for the given differential equation, that is higher order differential equation with the given initial condition. Those are known as initial value problems. So we can easily solve by using the Laplace transforms any type of higher order initial value problems. So before that, to understand in a better way, so first of all we must know what is the Laplace transform, what is the definition of the Laplace transform, what are the different functions when we apply the Laplace transform, what we are going to have. But what does Laplace transform do here? When we apply to the differential equations, the Laplace transforms, it converts one function into, that is a differential equation, into algebraic function. And from there onwards, while applying again the inverse Laplace transform, it will give the general solution, that is the complete solution of a differential equation. Okay, and it is Laplace transform is an integral transformation. It's just like Laplace transforms and the Fourier transforms. These both are the integral transforms. So now today we are going to discuss the Laplace transform. Let us start with what is the definition of the Laplace transform. Okay, so let us take a look at this one. This is the definition of the Laplace transform. So as you know, the Laplace transform is an integral transformation, as I told you already. Just like the Fourier transform, the Laplace transform is also an integral transformation of a function here is f of t from the time domain. Okay, the Laplace transform when apply on the time domain, it converts the time domain into frequency domain. Okay, into time domain into frequency domain, that is a complex frequency domain. So, and given by, we just denote here the frequency domain as a capital F of s and time domain as a f of t. Now, when we apply the Laplace transform, that is L of f of t, and it is denoted by the Laplace transform when we apply it on a function of t, so that will denote with the Laplace transform of f of t. So, the result, the main formula here, the integral formula like this, that is integral 0 to infinity e power minus st f of t dt. So, and the result of this one, with we are going to get in terms of s. So, that is why we will denote this, the result, with the function of s. That is f of s is nothing but just it's a function of x, like f of x, f of y, g of x, something like the function of x is nothing but in terms of every function in terms of, you will get like sin x, cos x, e power x, x by x square plus 1, like this we will get. Like that only we result, the final result, after taking that, after solving this integral, where the final result you will going to get in terms of s, like s by s square plus 1, a by s, s by a. So, like this you will get something in terms of s. That's why we denote the result when we apply the Laplace transform on f of t, the function of t, which is known as the time domain. When we apply on that, we will get the result in terms of s. So, that's why I denote that f of s. Here s is a real or complex number. Okay, it's a s is the real or the complex parameter. Okay, so it's known as a two-sided or a bilateral Laplace transform of the function f of t. So, when we apply this Laplace transform, only when the integral of this one is exist. Okay, when we apply the Laplace transform, not for every function we can apply the Laplace transform, only whenever we can apply the, provide that the integral is exist. See, in order to understand when we apply the Laplace transform to the different functions, you have to know the fundamentals of the integrations. So, that means what is the integral of x power n plus 1. Okay, what is the integral of e power x is e power x. What is the integral of e power ax? E power x by x. E power x by a. And what is the integral of sin x minus cos x? Integral of cos x sin x. Like this, we need to know some few differential and integral formulas. For the differential also we have to know, we should have a few fundamentals of differentiations and integral formulas. So, let us take a look at the first one. So, when we apply the Laplace transform to the different elementary functions here. So, let us take a look at here. As we know already, what is the formula to the Laplace transform of f of t? That is L of f of t is equal to integral 0 to infinity e power minus st f of t dt. Now, let us take a look at what is f of t. I am assuming here f of t as a k. Okay, let us substitute that in f of t is equal to k. So, since it is a constant, so I can take that constant out, and now I apply that integral e power 0 to infinity e power minus st dt. So, as you know the integral formula e power ax, something like e power minus st by minus s from 0 to infinity. So, when we apply that, you can take this parameter, the outside of this one, and apply the e power minus infinity, the upper limit minus lower limit 0. So, that is e power minus infinity is 0 and minus k by s into this value is 0, e power minus infinity, the exponential up to infinity, that is as 1 by infinity you can write 1 by e power infinity. E power infinity is infinity, 1 by infinity is 0. So, minus e power 0, that is 1. So, that is gives, so minus into minus plus, that gives k by s. So, you can see the result, that is k by s, where s is the parameter. It may be a real or complex, that is s greater than 0. Now, similarly, take a look at the second one. Let f of t is equal to e power at. So, let us apply again. What is the Laplace transform of e power at? So, this is gives the Laplace transform of e power at. Okay, what is the Laplace transform of e power at? So, this can be written like e power 0 to infinity e power minus s. Okay, so this can be, you can take the common and we can add this like if I take the minus common here, so I can use here If I take the minus common, so then I will get, see here, minus e power minus of s minus a t dt. So now as you know the e power x integration, e power x by a, so like e power minus s minus a t by minus of s minus a. Okay, integral 0 to infinity. Now if I take this minus of 1 by s minus a, take it out, e power infinity for the upper limit, that is 0 minus e power 0, it's 1. It's 1 by s minus a. So this is the Laplace transform of e power a t. So as you can take a look at the answer here. So this is 1 by s minus a. This is the Laplace transform of e power a t, and here you can take a look at s is greater than a. We need to consider. Next, second one, like L of t power n. So this is one of the important one. What is the Laplace transform of t power n here? So now you can take a look at directly. So you know the Laplace transform of this L of t power n. What is the Laplace transform of t power n? Input we in place of f of t, this t power n. Okay. So now what we are going to do, in order to integrate this one, so we put in place of this st, we use some another variable as st is equal to k. So now differentiate that, there you will get the dt is equal to dk by es. So substitute in that, as you know st is equal to, we are putting the new variable here, the k, just I put here. Now as you know the, what is the, from this st is equal to k, from this t is equal to k by s. Okay, t is equal to k by s, just put here. Now we can write k by s whole power n, and dt is equal to dk by s. We'll substitute this here. Okay, so the next, so what you can see here, so now after taking this, after the integration, and you can see this s power n and into s, so that can be taken out, s power n plus 1. Now integral 0 to infinity, now e power minus k, and this is k power n, so we can write like this, okay, in the dk. So now in order to understand this one, so how are we getting this one? So this is exactly in the form like 1 by s power n plus 1 integral 0 to infinity e power minus k into k power n. In the previous slide we have k power n. Now what I am doing, I am just adding and subtracting 1 here. Why? In order to get it just exactly looks like the gamma function. What is the gamma function? The gamma function can be read, it's a one of the type of special functions we can use in order to integrate some complicated integrals like in this form, like gamma n is equal to e power minus x into x power n minus 1 dx. Okay, so you can see this, this is also similarly in this form, integral 0 to infinity e power, in place of x we have the k, it's not a problem like here. So if it has n, we can write the gamma n, in place of n here we have, so this can be written as a 1 by s power n plus 1 gamma n plus 1. So this is what we can write by using this gamma function. Okay, so which is known as a gamma function. Okay, so from this this integral we can write it as a gamma n plus 1. That is what you can see in this one here. What you can see this, so this can be written gamma n plus 1. So here n is greater than minus 1 and of course s greater than 0. So gamma n plus 1. What is this? The Laplace transform of t power n is equal to gamma n plus 1 by s power n plus 1. Now what we can do, so there is a relation between the factorial and the gamma functions. So that is gamma n plus 1 is equal to, okay, n factorial. So gamma n plus 1 can be written as a n factorial. So gamma n plus 1 can be written like n factorial. So this is in terms of gamma n plus 1. When we use this and when we use this one, so this function, this formula, the Laplace transform of t power n, we can use for the integers, like for n is equal to 1, 2, 3, 4, 5, whatever it may be. As you know, the 3 factorial is 6, 2 factorial is 2, 1 factorial is 1. So when we can apply this formula, and this one we use, okay, this one we use whenever we have the n values like 1 by 2 and 3 by 2 and the 5 by 2. For these type of values we use this formula, since we know that gamma half value is equal to root pi. Okay, gamma half value, gamma 1 by 2, gamma 1 by 2 is root pi. Okay, so you can write now this is from the gamma function we can know that gamma 1 by 2 is equal to root pi. So gamma 1 by 2 value is a root pi. Similarly from this we can write gamma 3 by 2 also. But how? So whenever for the integers, as you know the gamma function, there is a relation between the gamma function and the factorial, that is gamma n is equal to n minus 1 factorial. Gamma n is equal to n minus 1 factorial, or we can write the gamma n plus 1 is equal to n factorial. So we can write like this. So that's how we can write this gamma n plus 1 as a n factorial. Okay, so can you understand this? Gamma n plus 1 is equal to n factorial we can write, and this formula we use whenever the n value for the positive integers like 1, 2, 3, 4, 5, so on, like this. For the, as you know, the 1 factorial, so is 1, 2 factorial, 2, 3 factorial, 6, like that, 4 factorial. We can use this formula to find the Laplace transform of the t power n. And for the n is equal to 1 by 2, 3 by 2, 5 by 2. So, but how can we find the value here? We can use a formula, one formula we have here. The gamma n plus 1 is equal to n into gamma n. This is the formula we can use, and similarly by using this formula we can write gamma 3 by 2 is equal to, we can write this gamma 3 by 2 as gamma 1 by 2 plus 1. From this formula we can write 1 by 2 gamma 1 by 2. Okay, so we know this gamma 1 by 2 value is root pi. So when we apply this one, so we will get the gamma 3 by 2 value is root pi by 2. Similarly gamma 5 by 2 also we can find like 3 by 2 into gamma 3 by 2. Since we know the gamma 3 by 2 is root pi by 2, so 3 by 2 into root pi by 2, that is 3 root pi by 4. So like that we can find the gamma values for these type of values, like gamma 1 by 2, gamma 3 by 2, gamma 5 by 2, gamma 7 by 2, like this we can find the values. And for the factorials, whenever the positive integers, we can use this formula, that is Laplace transform of t power n is equal to n factorial by s power n plus 1. So let's move to the next one. So when f of t is equal to cos at, the trigonometric function, what is the Laplace transform of cos at? Here, so when we apply using the fundamental formula, so in place of f of t, if we put cos at, so the formula will be like this. For this one, we need to know one formula. Okay, so like the direct formula we have, when the functions like in this form 0 to infinity, e power minus ax cos bx dx. For this formula, we can directly write one formula. So that is a by a square plus b square. This is the direct formula we have. So we can apply this one. Otherwise, we have one more integral formula. So that is, so not for the limits, whatever the limits we have. So we can apply that is integral, the direct general integral e power ax cos bx dx. This formula we have like e power ax by a square plus b square a cos bx plus b sin bx. Okay, so this is for indefinite integral. This is the formula we can use. Either we can use for the limit 0 to infinity, we can use this direct formula, or we can apply this one. So by applying this one, we will get the step like this, e power. Here you can see, imagine this a, in place of a we have a is equal to minus s and b is equal to a. So we apply the formula like this formula, like e power minus at by s square plus a square minus s cos at plus a sin at. So let us, after applying that, taking the upper limit, e power minus infinity, so that is e power, first step, that is for the upper limit, that is 0, e power minus infinity is 0, 0 into anything, 0, minus of e power 0, in place of t we have to put those limits, infinity and the 0, 0 e power 0 is 1, 1 by s square plus a square, so minus s, cos 0 is 1, sin 0 is 0. So like this we can apply. So now minus of minus plus s by s square plus a square. And this is how we can find the Laplace transform of cos at, that is equal to s by s square plus a square. So now let us take a look at f of t is equal to sin at now. So now in order to get this one, so that is the Laplace transform of sin at. So now again, this is the another formula we have, e power minus integral 0 to infinity e power minus at sin bt dt. So we can directly write one direct formula because it is almost similar to that. So that is, this can be written as b by a square plus b square. This formula directly apply, or we can apply one another integral formula. So like this, e power ax sin bx dx is equal to e power ax by a square plus b square a sin bx minus b cos bx plus c. So this is another formula we have. We can apply either this directly or we can apply this. When we apply this formula, so we'll get this, the next step like this, e power minus at by s square plus a square. You can see in place of a we have minus s, in place of b we have a. So when we apply exactly this formula on this, so we'll get the step like this. In the next step, e power minus infinity, that is 0 minus of e power 0 1 by s square plus a square. Now sin 0 0 minus a cos 0 1, a into 1 this is. So there you will get the formula for the Laplace transform of sin at, that is s by s square plus a square. So this is the Laplace transform of sin at is equal to 1 by s square plus a square. Okay. So now, so these are the properties we have. Okay. So these are the properties we have. So we will discuss deeply about these properties, that is a Laplace transform of different properties we have here. So these properties we will discuss in the next class. Like this first one, the linear property and the first shifting property, change of scale property. Like this we have so many properties which by using these properties we can minimize the difficulty level of the finding Laplace transform of different functions. Not only the few fundamentals, that is the Laplace transform of few functions we already discussed, that is the Laplace transform of k is equal to k by s. Like from that we can find Laplace transform 1 is equal to 1 by s, Laplace transform 2 is equal to 2 by s, and of course the Laplace transform t power n also we have discussed, and Laplace transform sin at and the cos at. And so not only that, for the different functions, like any combinations of the trigonometric and exponential and the combinations of trigonometric algebraic functions, like this, for such functions, how can we find the Laplace transform? That we will discuss in the next class along with these properties. These properties will definitely help us to find the Laplace transform of some different functions by using already what we already know about the fundamentals. So what we already know about some different elementary, when we apply the Laplace transform to some elementary functions, by using those and by using along with these properties, we can simplify the finding the Laplace transform of some different functions also. That we will discuss in the next class. That's all for today. Thank you.